In this video, I introduce denoising diffusion implicit models for faster generative process. Denoising diffusion probabilistic models simulate a Markov chain for many steps, for example, 1000 to produce high-quality samples. Denoising diffusion implicit models use a non-Markov diffusion chain with lesser steps, for example, 100, to speed up generative process as shown here. This Markov chain xt only depends on xt minus 1. This non-Markov chain xt depends on both xt minus 1 and x0. Given a sample x0 from a distribution qx0, DDP models learn a model distribution p theta x0 to approximate qx0 as shown here. This is the joint probability of x0 to xt that is calculated by using prior and reverse diffusion transition, where x1 to xt are latent variables. The model parameters theta is learned to fit the distribution p theta to qx0 by maximizing a variational lower band on the log likelihood, as shown here. Where Q is a conditional inference distribution over the latent variables x1 to xt. If a Markov chain with Gaussian transitions is parameterized by a decreasing sequence alpha 1 to alpha t, the forward diffusion process Q is defined as here. The transition is calculated from this normal distribution. The covariance matrix to ensure positive terms on the diagonal. A marginal of the forward process is defined as here, where xt is a linear combination of x0 and noise E as shown here. If alpha t tends to 0, Q converges to Gaussian for all x0 as shown here. If all the models are modeled as Gaussian with a trainable mean and fixed variance, the DDP model objective is defined as a square matching, as shown here. For x0 sampled from qx0, ET sampled from a normal distribution, xt is computed from x0 and E. The model predicts ET from xt. DDP model objective L gamma only depend on the marginals Q, but not directly on the joint Q, which allows DDI models to find non-Markov reverse diffusion process with the same objective function as DDP models. Since many inference distributions may correspond to the same margins. A family of inference distributions correspond to Q sigma, defined as here, where sigma is the index and Q sigma is calculated from this normal distribution, and for t larger than 1, the reverse transition is calculated from this normal distribution. The mean here ensures Q sigma is calculated from this kind of normal distribution with this mean and this variance. Using Bayesian law, the forward process is written as here. The trainable reverse diffusion process p theta uses each reverse process diffusion transition p theta t to approximate the reverse diffusion process Q sigma. Given a noisy observation xt, DDI models first predict the corresponding x0 and then use x0 and x2 to obtain a sample xt minus 1 through the conditional posterior Q sigma. Using this formulation, the prediction x0 is computed from E theta t in this formulation. The generative process P theta t with a fixed prior P theta is defined as here. For t is 1, P theta calculated from this normal distribution. Otherwise, use this Q sigma. The Gaussian noise at t is 1 is to ensure that the generative process is supported everywhere. This is the DDP model and this DDI model. The iterative process of denoising diffusion process is defined as here. Namely, we calculate xt minus 1 from 3 terms. First is a predicted x0, second term is a direction pointing to xt, and random noise as explained as here. Where et sampled from normal distribution and alpha 0 is 1. All sigma values share the same model E theta, namely unnecessary to retrain the models for each sigma. Denoising diffusion models learn reverse process of diffusion process, which generate arbitrary images starting from Gaussian noise distribution. The denoising process is required to use the same number of steps as the forward process, which is very slow. DDI models do not depend on the specific forward process as long as the marginal Q sigma is fixed, so that DDI models accelerate generative process with a small number of time steps. For example, as shown here, we can calculate x1 directly from x3, skip this x2. For more details, please check with these references. Thank you. Bye.